So to help us understand how to define the Fourier integral representation of a function, let's remember the structure of the Fourier series of a function f of t, which has period of 2 pi, or probably has an arbitrary period of 2p. So recall that. Given a 2p periodic function, f of t, its Fourier series so I'll have f of t is given by a naught over 2 plus summation n from 1 to infinity of an multiplied by cosine of n pi t over p plus bm sine of n pi t over p and these Fourier coefficients are given by a naught is 1 over p integral from minus p to p of f of t dt, and then an is given by 1 over p integral from minus p to p f of t times cosine of n pi t over p dt, and bn is given by 1 over p integral from minus p to p of f of t sine of n pi t over p dt. I remember for this case, here n is 1, 2, 3, all the way up to infinity. So from what we discussed on Fourier series, this is not a very new formula or a new result. So for any given function which is periodic of period 2p, then we can always represent it as a Fourier series using this formula here. So this happens when the function f of t is periodic. But sometimes we may be interested in representing a function f of t, which is not necessarily periodic on the real line or on the entire t-axis. So in such cases whereby the function f of t is not necessarily periodic on the t-axis, we'll represent it using what we call the Fourier integral, provided that the function f of t and its first derivative are continuous, piecewise continuous in every finite interval, and the integral from minus infinity to infinity of the absolute value of the function f of t exists. So in such cases, we have a different structure on how to represent f of t. So the question is that so probably we can call this one formula star. Let's call this one star. Given that f of t is defined on the t-axis, so that's the main question. Assuming that on the t-axis or simply on the real line, the function f is not periodic, is it possible to represent f as a Fourier series? The answer to this question is no. So when the function f is not periodic on R, or f of t is not periodic on the t-axis, then we can no longer express f of t as a Fourier series, but we can express it as a Fourier integral in terms of Fourier integral representation. So then now we define what we mean by Fourier integral representation of a function and see how that can help us to define Fourier transform of a function f of t. So we can call it a theorem. Fourier integral representation. So there are two conditions that must be satisfied by the function f of t. So suppose that f is a piecewise smooth, now when you say piecewise smooth, is the same thing as saying piecewise continuous. In every finite interval, or you can say on every let the integral from minus infinity to positive infinity of now, when you say this integral is less than infinity, it will simply mean that the integral exists. So saying that the value of an integral is less than infinity is the same thing as saying that the integral exists. Or when you carry out the integration, you get a number. Then f has the following Fourier integral representation. So we write this as f of t is given by the integral from 0 to infinity of a of omega multiplied by cosine of omega t plus b of omega multiplied by sine of omega t and then you integrate with respect to omega. I remember this t lies between minus infinity to positive infinity. Where for all non-zero values of omega, a of omega is given by 1 over pi integral from minus infinity to positive infinity of f of t cos of omega t dt, and b of omega is 1 over pi integral from minus infinity to positive infinity f of t multiplied by sine of omega t dt. So that's what we call the Fourier integral representation of an arbitrary function f of t, which is not necessarily periodic on the t-axis, or which is not necessarily periodic on the real line. So that's the structure of the Fourier integral representation of f of t. Now, once you understand this Fourier integral representation in terms of the sine and cosine, we can now be able to define in general the structure of the Fourier integral representation in terms of the Fourier transform and the inverse Fourier transform, just the same way we discussed about the Laplace transform and inverse Laplace transform. So in more general, terms we use the complex representation to define the Fourier integral representation. So we will give the structure of the Fourier complex representation of the Fourier integral representation that will actually be used to define the Fourier transform and inverse Fourier transform. So this is what we mean. Fourier integral representation of f of t So we are going to give two powerful formulas. One which will define the Fourier transform, and the other one will define the inverse Fourier transform. So the Fourier transform of a function f of t which will be a function of omega is given by the integral from minus infinity to positive infinity of f of t multiplied by negative I omega t dt call this 1 and 2 we have the inverse Fourier transform will be given by f of t, which is given by 1 over 2 pi integral from minus infinity to positive infinity f of omega e raised power I omega t d omega. In both cases, So t and omega are any real numbers. And by default, we know that I is the square root of -1, a complex unit. So when it comes to the integral representation of a function f of t, we'll be taking the structure of Formula 1 and Formula 2, where Formula 1 defines the Fourier transform of the function, and Formula 2 defines what we call the inverse Fourier transform of f of omega. So please mind your handwriting. When we are defining the Fourier transform, this is capital F, and the function itself we write small f. So Formula 1 and 2 are called a Fourier transform pair. Formula 1 and 2 are what we call a Fourier transform pair, where Formula 1 is what we call the Fourier transform, and Formula 2 is what we call the inverse Fourier transform of the function f of omega. So one, yes?
Could you scroll up a bit? My connection was a bit messed up, so I missed some of what you wrote.
Up to what point?
There.
Okay, good. So you can say as he copies, let me save on time and space. So Formula 1 is called the Fourier transform of the function f of t, and this Formula 2 is what we call the inverse Fourier transform of omega. Inverse Fourier transform of capital F of omega. So the formulas come out in more or less the same structure as those for Laplace transform and corresponding inverse Laplace transform. For Fourier transform, we use capital F. And remember, when you are defining the Laplace transform, we used S. So this time we are picking omega. But you are senior enough to know that that cannot never confuse you. Even if you replace omega by S or replace omega by a different letter, say K, you can as well define the same Fourier transform. These letters are usually done. So one is a Fourier transform of f of t to inverse Fourier transform of f of t. And together 1 and 2 are what we call a Fourier transform pair, which means one formula gives you the transform, the other formula gives you the inverse transform. But it should be noted that there is no universal way of writing this Fourier transform pair, because the nature of this coefficient, 1/2 pi, different people, different textbooks can give the formulas differently. Some can decide to put 1/2 pi in this formula 1. So we can decide to put the coefficient 1/2 pi in this formula 1 and avoid putting it in formula 2. It will still be true definition of a Fourier transform pair. Or some people will put the coefficient of the first formula before the integral sign, 1/√2 pi, and also put 1/√2 pi in the second formula. It will still be defining a Fourier transform pair. So let's just put that one clear so that when you read different textbooks, you don't get confused. But to remove confusion, all our computations in terms of the Fourier transform and the inverse Fourier transform, we are going to stick to the definition given in 1 as the Fourier transform and definition given in 2 as the inverse Fourier transform. But also different forms of the same formulas exist. So I'll say no fixed there is no universal convention for writing the Fourier transform pair e.g. some authors write the factor 1/2 pi in the first formula of the integral while others one over 2 pi in both formulas. So the structure of the formulas may not necessarily be what you have written. So some people will decide to put the factor 1/2 pi in the first rather than the second. Or some people will decide to put the factor 1/2 pi in all the two formulas. And some other people can as well have different variations in terms of where they place the factor, where they place the function e raised to -i omega t. So when you meet such different variations, please know that we can as well have such definition of Fourier transform pair. But for consistency, we are going to stick to the definition given in 1 and 2. So for instance, we can say the Fourier transform of a function f of t, which is f of omega, is 1 over root 2 pi minus infinity to positive infinity f of t e raised power negative omega t dt, and you define the inverse Fourier transform of f of omega, which will give you f of t is 1 over 2 pi integral from minus infinity to positive infinity capital F of omega e raised power I omega t, the omega. Here omega lies between minus infinity to positive infinity. Also t lies between minus infinity to positive infinity. So this is another way of writing the Fourier transform pair. It's still okay. But to avoid confusion in different ways of writing the formulas for Fourier transform and Fourier, inverse Fourier transform, we are going to stick to 1 and 2, where we are putting the factor 1 over 2 pi only on this second formula, but the first formula, we don't have that coefficient. So for consistency, we will stick to the definition given in 1 and 2. In the definition, of Fourier transform, and inverse Fourier transform. I remember collectively this is what you're saying, Fourier integral representation. Or Fourier transform pair. So because of different natures in definition of the integral representation, Fourier integral representation or simply the Fourier transform pair, let's have one convention that we're going to stick to when it comes on solving problems on the Fourier transform and inverse Fourier transforms. So I give you 5 minutes break. When you come back, we'll do examples on how to find the Fourier transforms.